London is her favorite city on the planet.
Let's see, do we get indication that we're recording?
Yes.
Yep.
There we go. Okay, we are recording. That's what I'm looking for.
Okay.
Okay, so let's see, am I in frame? I guess I gotta talk to that. Okay. Welcome everyone to the, what is this? May Northwest C++ Users Group. We've got Dan talking tonight on pricing equity options with mdarray. First off, I want to thank Microsoft for donating the room. And also want to thank Conan and JFrog for donating the Meetup account for us. And next I want, Chris has a couple of announcements for CPPCon, or one of them, so we'll do that. Hang on, I'll swing the camera over to you. All right.
Hi, all. CPPCon call for submissions just opened up. Be about 5 weeks or so that it's open. Call for volunteers should happen pretty soon also. So lots of stuff moving and shaking with that. CPP North will be in July. Call for submissions on that is closed, but I invite you all to come up to Toronto. It's a great time up there. So July is nice and hot. So.
Okay. And with that, we will turn it over to Dan.
Okay. Hi.
There's Dan. And take it away.
Okay, all right, well, welcome everybody to, we're finally meeting in person after 3 years, I believe. Just a little trivial factoid that I was actually the last scheduled in-person speaker in March 2020.
Oh, that's it. We should swap you and Peter. That would have been great.
Yeah, so I'm the first back. Maybe that's a dubious distinction, but anyway, here we are. But I'm just so glad it's over. At least we hope. Anyway, I think some of you know me, but in case not, and for you in TV land, my personal interests are more towards solving problems with modern C++ rather than, getting into the, the vast details of the language. And this in particular, font finance. Also, as a little bit of a shameless plug, I'm also working on a book on this subject, and it's due out later this year. Although if you're interested, some of the chapters are available on the in early release on the O'Reilly Learning website. I knew it'd be a lot of work. I didn't realize it'd be this much, but anyway. But now in this particular talk, what we'll do is look at how we can use mdarray, which is the owning analog of the much anticipated mdspan, to solve the problem of pricing options with lattice methods. Okay, so a little bit about mdspan first. It's slated to be released with C++ 23, and just as an aside, don't throw tomatoes at me when I say this. It has some of the nice features of Valoray, which personally I found to be very, very useful, but unfortunately it came with issues. But with mdarray, you can do some of the things you could do with Valoray, but we won't have the some of those troubling matters that came along with Valoray.
Does MD mean multidimensional?
Yes.
Okay.
As far as I know, I wasn't there at its creation, but so we can look at an example here. The cool thing about mdspan is you can impose a multidimensional array structure on a one-dimensional container, for example, an STL vector, and do it all without tiers. So what it gives you is a view to the existing data, so it's non-owning. So, for example, if I have a simple vector here of 6 integers, I can impose on it a 3x2 matrix structure. I'm going to use, I know that there are technicalities, there's difference between matrix and array, but I'm just going to use the term matrix, even though we're not multiplying them or anything like that. So when you do this, you call mdspan, give it the data in the vector, and it says, I want 3 rows and 2 columns. And lo and behold, you get something that looks like a matrix. So this is pretty cool. Now, for a little bit of terminology, the rows and columns are referred to as extents. And the number of rows and columns are accessed by the index of each extent. So in this case, we have 2 extents, rows and columns. The first index is 0 for the rows and 1 for the columns. And then the total number of extents is referred to as the rank. So for example, if I access the first extent, it's going to return 3 for 3 rows. And likewise, the second extent, or 0 index, because we're in C++, will return 2. And then the rank will give us also the value 2. This can, of course, be expanded to an arbitrary number of dimensions. We will first concentrate mainly on the 2-dimensional case, which is what we need for the model we'll be discussing. But anyway, as a matter of record, for higher order multidimensional arrays, the rank would be greater than 2. Also, the extent sizes for both mdspan and mdarray can be dynamically allocated, and I'll be talking about that here in a little bit. I guess I should look at the camera. Sorry, this is all new to me. Just one side note here, if you are mathematically inclined, which is more my background, the term rank here as applied to mdspan and also mdarray is not the same as the mathematical definition of the rank of a matrix. So this might unfortunately seem a bit confusing, but it's something that you'll want to be aware of if you're working with mathematical applications. Okay, so now what if we don't know the data a priori like we did before? We had the data given to us in a vector, but what if we don't have that? And furthermore, what if we want to generate the values and place them, say, in a 2-dimensional array format, which is where we're going with this? Well, the answer is mdarray. This is expected in 3 years, so with C++ 26, but it is available now on GitHub under the Cocos site. They've put it under a namespace stood experimental, but we will use its kind of a de facto standard, the namespace stood X as an alias. Just as, again, kind of a side note, I've been working with the code that's available on GitHub, and so far it works fine. So, I mean, you should be able to try it out, and I'm assuming it's close to being complete. Of course, there's always that nagging, lingering 20% that takes 80% of your time. But anyway, as far as I've been able to tell, it works out, or everything seems to work fine. Okay, so what we're going to do is we're going to apply mdarray to an example where we don't know the data in advance. And instead, as I mentioned at the outset here, that the values will actually be generated by a model that is commonly used in quantitative finance. Also, the number of rows and columns can be allocated dynamically. and that it would be similar for mdspan. But as you can see, we just create an instance of mdarray. It's going to hold integer types, and we are allocating the extent, so the number of rows and columns dynamically, but there are two extents. So again, think rows and columns for some arbitrary positive integers, m and n. You can use other types, size t, unsigned, whatever you like. So dextents stands for dynamic extents. And so in this case, what we're doing is we have two dynamic extents of int type, where m and n, again, are arbitrary positive integer values. Note here that we can't use ctad because we don't know the type yet. We don't have, for example, a vector with the stuff in it already. So we have to explicitly tell it that it's going to be holding integer types.
Could I ask a quick question?
Sure.
I don't know the abbreviation CTAD that you just used. Can you tell me what that is?
I'm sorry, class template auto deduction.
Got it. Thank you.
So I don't know if you know, just in this case, note that I didn't give it a template parameter. Why? Because these are integers and it knows. Okay, so now we will get into binomial lattice option pricing. Just an overview of options trading and the model. We'll go through that hopefully quickly, and then we'll get to the C++. I think most of you here are quite young, so you don't remember October 1929, but I remember when this happened. We ended up in a Hooverville until my family found work picking artichokes down in California. That's another story from the day. No, seriously, before proceeding with the C++, again, I'm going to go through kind of a quick discussion of what equity options are and what the binomial lattice model is that we will eventually then implement using mdarray. Okay. So some of you may know this, some of you may not, but an equity or a stock option, equity is essentially a fancy way of saying stock, is a derivative security. So it's based on the stock. The stock is called the underlying security, and then the derivative does stuff on top of it, like an option. And in particular, what an option does is it gives the holder of the option contract the right to buy or sell the stock at a set price, which is called the exercise price, also called the strike price, on or before the expiration date. And there are two types of payoffs. One is a call option. That means it's an option to buy, and a put option is an option to sell the stock. So if we let S be the underlying stock price, could be IBM, could be, say, a S&P 500 index. It could be all kinds of different underlying securities that you can have options on. But we let S be the underlying stock price, share price. And then we let X be the exercise price. And so if the payoff is on the option is exercised, you will receive for a call option the value S minus X. So if the share price is greater than the exercise price, then you buy it for X, turn around, sell it for S, and you make a profit. That's the idea behind it. And similar for a put option where you're selling. Okay. Also, a little more terminology here. An option is said to be in the money if its payoff is positive, at the money if the S and X are equal, and out of the money otherwise. So as an example, consider a call option we are at time T sometime before the option expires. And we have a strike price of 95. So the solid line that you see here is the value of the option as a function of the underlying stock price. The dotted line is what's called the intrinsic value, and that's the payoff if you exercise the option. So if you're up here, you're in the money. At 95, that's the strike price, also called the exercise price. Easier to say strike price, I found when I was rehearsing for this. From there and below, the value of the payoff is zero, so you'd get nothing. And this is, and one more thing is, this dotted line is called the intrinsic value. There's also a time value. And that's the difference here between the dotted line and the solid line. So what this means is you might be out of the money, the payoff might be worth nothing, but there's still time for it to go into the money. And so that still gives the option value. One final point, though, is that a lot of times the option is not exercised, but it's sold. So it's worth something in the market itself. And in fact, there are cases where it is not optimal to exercise the option. It's better to close out. And this is an example here because the value is always greater than the payoff. This is typical for a call option on a stock not paying a dividend. But there can be cases where things turn around. For example, if you bring a dividend into the picture, then we'll talk about in a minute. But if the option allows early exercise, then it can be optimal to exercise the option. Okay, so far we saw on the previous slide how call and put options describe what will happen if the option is exercised. What we want to know now is when can we exercise an options contract? And again, we'll use the option or the example of a call option. Okay. So what we'll do is we'll look here at some hypothetical price paths of some stock. And we're going to look at a call option with a strike value of 105 from sometime T0, which is now, up to some time in the future, capital T. And so what we want to know is when can we exercise the options contract? Okay, there are two basic types. There are European options, and that means they can only be exercised on the expiration date. So that means if you were in the money at expiration, you can exercise the option here, take the difference. So, well, if you exercise it, you buy at X, sell at S, which is greater, and then you make a profit. If you are out of the money, then the option just expires worthless. An American option, however, can be exercised any time before or on the expiration date. So that means we can exercise at these points here. And so if you're lucky and you're way up here, and if it's a type of option where it would be optimal to exercise, well, yeah, you'd do pretty well. It's not a high probability of, being able to pick out the highest point. But anyway, if you could, it would be great, wouldn't it? On the other hand, either type can be bought or sold in the options market at any time. So even though you can't exercise European option before expiration, you sell it and make a profit. And similar for an American option. So instead of exercising, you might choose to sell the option there. Or you could sell at these points. And again, this could be a European or an American option, doesn't matter. So the goal here so at t equals 0. That'll give us an idea of what it's worth in the market and what we could get.
It said the video stopped working. Try unplugging and plugging it back in.
Okay, should I
It looks like
pause?
No, I think the,
crashed because those went off too.
The video froze with the,
All of a sudden pulled.
yeah.
Can you change slides? Change slides, do we see it up there?
Yeah.
Yeah, we see this.
Okay, we've got that. So
So we
we,
at least have the slides.
yeah, keep going. The video's down, but
Okay, is the audio working?
Group doing something, so she might be over there.
Yes, the audio.
Going to be 1 foot in.
Great, thank you, Robert.
Oh, the audio is being recorded?
okay, let's just keep going and I'll see if I can get the camera going.
Okay, that's fine. It's just I want to make sure that
Yeah,
the audio is getting recorded. So, okay, so what we want to do with where we're going with this thing called a binomial lattice, it's a model that will calculate a fair price for example, a call option today at t equals 0. Why? Because we might want to trade these things in the market and buy and sell them. So we need to get an idea of how much an option is worth. Also, when running risk, so the institutional investors and investment banks, so forth, if they hold portfolios of options, they're also going to need to value their portfolios as market conditions change or they shock their portfolios to see what would happen under worst case scenarios. So in that case, they want to have a way of pricing the option and getting an idea of what its value is under different market conditions. Just a note here, the price of an American option is never less than a European option. And the reason is that the American option offers you the ability to exercise before the expiration date. So there's value that's attached to that as well. Okay. Now, European equity options can be valued using a closed form solution, and some of you may be familiar with the Black-Scholes formula. So there's really not a need to use binomial lattices to price European options, although you can do it if you want. The binomial lattice is essentially an approximation of the Black-Scholes formula. And all the theory comes out of the Black-Scholes theory. Or I'm sorry, all the results, the computations that we'll see soon. An American option, on the other hand, requires numerical approximation. There's no closed formula like Black-Scholes. There isn't one for American options. The reason is we need to check for optimal early exercise. So we want to know, is it worth exercising an option at a certain time? It may or may not be the case. But it's
What closed form means?
closed form means you can write a function like f of x equals x squared plus 2.
Okay,
An approximation is you converge to a result.
I understand.
The binomial lattice pricing model is in particular well suited for pricing American options. That's one place where it is quite often used. And as a result, this is where mdarray can help us, as we will see. Also, as an aside, boost multi-array can also be used. In fact, I've used that in the past for this purpose. It works, it's fine. But the thing is with mdarray, we will have the tool available to us in the C++ standard library. We won't need an external library for it. Okay, so there are overall two steps involved. The first one is we need to project prices forward. So you saw in the earlier slide, we had the hypothetical scenarios of the stock price movement. It's a similar idea with lattices, except that they are deterministic. And so,
Can I ask you what a binomial lattice is?
oh, I'm going to show you right now.
Okay.
So, yeah, I should have said that. That's what's coming up. So we have 4 time steps and 5 time points because we're going to include this initial node here at 0. So suppose we have a call option, its time to expiration is 1 year. And what we're going to do is we're going to take that 1 year and we're going to chop it up into smaller increments. So for this demonstration, we'll just use 4 time steps. So each time step will have a length of 0.25. Let's suppose the initial equity price, what we see in the market today, is 32. And we also know that the volatility of the stock it's a measure of how risky the stock is based on the fluctuation in the returns. That's incorporated in the volatility. It's essentially a standard deviation. The annual risk-free rate, which is usually you get from US Treasury securities, and we'll assume a continuous dividend rate of 7.5%. Now, in reality, dividends are paid on a certain date. So it's a set amount, there it is. But for modeling purposes, often the way this is done is it's assumed that the dividend will be paid out continuously over 1 year. So we will use that assumption and suppose that that dividend rate is 7.5%.
Can I ask another question?
Sure, yeah, go ahead.
Normally you would have a dividend being a continuous number if you have computational problems, but with computers, you don't have these problems. So why not have them in there as a step function?
There is a way to do it, but it would complicate things and kind of detract from the point of using mdarray. That was my idea. And but this assumption is still often used in practice,
Okay.
especially when you're dealing with longer term options. But it gets into a different area, dealing with like annuity contracts and things like that. Okay, so we're going to start with our stock price of $32. That's what it is in the market today. What we're going to do is we're going to project the prices out with up and down moves. Now, there's a little bit of math here. It's not too complicated, but we're going to multiply this price by an up value and a down value defined as you see here. And these formulae do not just come out of thin air. As I said before, they ultimately come from the Black-Scholes theory. And so if we apply those to $32, we'll see an up value of $35.37 and a down value of $28.95. So in the first step, our up movement leads to the price you see here and down movement to $28.95. We're going to continue this process. We're going to keep going until we hit the expiration date here. So that's part one. It's a 2-step process. The next thing we need to do is go back in time and we're going to calculate the discounted expected payoffs of the option. So this starts by applying the max function to each price at expiration. So, for example, the top node, we had a terminal price of $47.74, subtract $30 from it, and we get $17.74. Down here, for example, you're out of the money. You get a negative result, but it's the maximum. It's the maximum of the difference or zero. So the payoff is just zero, and the option expires worthless. Doing this for the rest of the terminal prices, that's what we get. That part is not rocket science. What we're going to do, though, we're going to move back now to the third time point. And so at each preceding node, what we're going to do is compute the expected value of a node here based on these two payoffs and a probability that is defined by this equation here. Again, all these values are known, so it's not an issue, just calculate it. These are all the exponential to little e's here. And so what you do, it's binomial, so you're going to compute 1774 times the probability of an up move, and then the down move, probability is going to be 1 minus p. So you calculate the expected value, but we need to discount back by a quarter of a year. And so for that, we need to hit it with this discount factor here. And again, we're just going to assume that interest rates are paid out continuously, so we can just use the exponential function. Again, it's often done in modeling, just to, it's called continuous time finance. Okay, so that gives us the payoff here of 1284. We're going to continue this for each of the previous nodes here. And then we're going to work back and keep doing the same thing until we reach the first node at t equals 0. So again, that's what we see today. And that the value of this, or this expected value here, gives you the price of a European call option seen today. And it just comes, again, from computing the expected values of the payoffs in the later nodes and then discounting them back by a quarter of a year.
How is this different than just undoing what we were looking at when we were moving forward?
When we're moving forward, maybe it'd be, if I use my laser. Going forward, we're projecting the underlying equity price. So we're going from 32, 35, 37, 39.08, and so forth, up to 47.74. That's the stock price. On the way back, what we're doing is we're computing the payoffs. So what will the option pay? Or what do we expected the payoff to be if we were to exercise it here?
Okay, gotcha.
Okay.
And then basically the 319 is the fair market price at the time zero.
Of the option contract.
So if the option is you can buy it for less than 319, it's a good deal. If
Yeah.
it's more than 319, it's a bad deal.
That's right. Yeah, essentially. Now, in fairness, you have to remember, though, this is a model. So,
Yeah.
and there are certain assumptions in the model that
your mileage may vary.
To be
Exactly.
aware of.
I have a question.
Sure.
On the fourth line of your slide, you're subtracting 30 from the 47.74.
Yeah.
Why are we subtracting 30 instead of 32, which was the original price of stock?
Because the exercise price is 30, X is 30.
Okay.
He's gonna pay 30 for it.
Okay,
If this is done iteratively, are the calculations done iteratively on
Yeah.
this? My experience with iterative calculations is you get killed by round off errors. Rather quickly, in fact.
well, that's why we use double precision. It's one reason. That's
Double
one reason.
precision is not good enough, so.
Well, in my experience working as a quant in finance, it usually did the job. So,
And the other thing too, you're not taking that many iterations. It's only like 4
well, so far.
so far. Yeah, okay.
I see people coming off, factor of 2 is their answer from working with 6-digit numbers because of accumulated round off error.
Yeah, it could be. I've just never seen a case of it in the financial practice. So I guess we're
No,
lucky.
I've run into this in aerospace. 6 digits doesn't cut it. 12 at least.
Yeah. Well, also keep in mind that, again, this is double precision. So even though it's, say, $32, that's 32.0000 and so forth. So there is decent precision. Okay, now,
Don't use float.
I'm sorry.
Just don't use float
Right, yeah.
or less.
13 and 1/3 digits.
Okay, so that was fun, but again, we could just use the Black-Scholes equation to get that value. But it's with American options where these lattice solutions are very useful. And recall that, why is this?
To undo the laser, I think.
Really? Oh, I didn't.
Hmm.
It steals your clicks. Now, if you're dealing with a computer that had more than one mouse button,
Okay. And that's right, with my clicker, it's no problem. I didn't bring it. Okay, so with American call options, remember that we need to check for optimal early exercise. And this is now where mdarray becomes really useful because we're going to need a numerical solution. So again, we start with the same payoffs at expiration. So nothing changes there. The first step is to calculate the discounted expected payoffs like we did before. But what we're going to do is we're going to compare it with the actual payoff. So for example, in this top note here at time 3, or the time step 3, recall that our expected value is 1284. But if we take the raw payoff, which is the value of the stock less the strike price, we get 1320, and that's greater. So we're going to replace the expected value here with the actual payoff. To do this. And then we just do the same for the rest of the nodes in the column. And again, here we have optimal early exercise because the actual exercise price is greater than the expected exercise price. So this means if we are in this state of the world at this time, then we would be better off exercising the option rather than selling it or waiting until expiration. And just as an aside, I don't know if I mentioned it early on, maybe I did. An American, just again as an aside, an American option with no dividend will never be optimal to exercise early. And in fact, it's going to be the exact same price as a European option. But because I brought a dividend into the picture here, we now have the possibility of early exercise. So we'll keep going. And again, here we have optimal early exercise. But down here, these are going to give us actual payoffs of 0. So we just stick with the expected payoffs. Keep going. And then at the initial node, it's the same idea, but now note that we have a value of $3.34, and that is greater than what we got with the European case, which was $3.19. So again, having that early exercise adds value to the option.
So can I ask a question?
Sure.
So you said like the expected was, so let's look at column 3, the top number. The
Mhm.
expected was 1284 and the actual was 1320.
Mhm.
But if you have an actual, how do you know which one of those 4 numbers or which one of those 4 options you're looking at?
It's all the same option. It's
Okay,
that the
so-
payoffs, the payoffs are different because the underlying stock prices are different. We're projecting out the prices.
You're kind of predicting the future, basically.
Yeah.
Okay, so you're still predicting future at this point. That's not an actual based on market data for that day.
That's right. Yeah, these
Okay.
are all projected prices.
If you wait, 6 months out, you can look at what the price is then, and then look at this comparison and see, is it worth it for me to buy it today? Exercise it early.
Well, it's what you're doing is you're saying as of time 0, if we have step 3 in the state of the world, it will be we should exercise the option. That's what it says. If we're actually in real time, then we go forward here, then all this is going to change.
Because 6 months from now becomes T0.
Exactly.
Well,
It's kind of funny when you're working with finance, you sometimes kind of feel like you're, doing time travel, but
Well, if everyone trading this uses this technique, doesn't it all kind of factor out to nothing? All you're gonna do is what the market does?
well, there are more advanced models that actually work off of the same theory. And they're more, this theory is ultimately based on the normal distribution, which is not necessarily accurate for stock returns because it doesn't capture the fat tail. So there are other methods where you can use different types of distributions like T distributions, QT, that sort of thing. So there's, these investment banks and so forth and hedge funds, they are going to hire people like Stephen, who graduated from the University of Washington Computational Finance program. And so they get involved in, the latest and greatest. So
It's essentially an arms race.
it is, yeah.
Well, and the other point here is not everyone uses these. And the investment banks all do, but not all market participants do.
There's that too. And also keep in mind that this isn't just for trading. As I said, this is useful for when you're running looking at your portfolio and analyzing risk. This could be perfectly sufficient for that purpose. Because what you have is you have a portfolio, so you have options. And then you're going to shock it with, say, like spikes in interest rates or the
U.S. government insolvency.
Yeah.
yeah, government insolvency, yeah. Or a 20% hit in the S&P 500 or something like that under these different scenarios. Or you can have random scenarios. And each time, along that path, you're going to be, well, I'd say for each of those scenarios, then you need a price. And so you can use a method like this to calculate that price. If you have an option, say that's expiring in a year, then you just apply you take the 1 year, divide it up and get the price. So that's under one scenario. Go to the next scenario, do it again. Go to the next scenario, do it again. And then eventually, if you're running a lot of simulations, random simulations, it's another way to do it, then you end up with a distribution of option prices. Or rather, you can get your P&L on the option. And so you can then see, you can go out to the left tail of the distribution and say, well, with 95% probability, this is the worst possible loss I will suffer. So that's another area where these are used. It's not just for trading. In fact, for trading, they're probably going to be using, again, the ones that hire people like Stephen, probably going to be using more sophisticated methods.
I have a question. In the marketplace, typically speaking, how does the number of outstanding options compare to the number of shares of the company? Say for stocks on the New York Stock Exchange, is it the number of options relatively small compared to the number of shares, or is it more substantial?
It's pretty big, but I don't know what the ratio is.
So it does vary by company. Some companies don't trade much in options. Some go.
That's true,
some go
yeah.
Absolutely crazy.
Yeah.
So in 2021, in late 2021, the outstanding notional value of the options, if you put all the options and you put all the shares, was actually notional, not the actual, the price value, but like the strike price. If you total all that up and said they're all going to go ITM, of all the options traded in the market exceeded the actual market cap of the market.
Oh, really?
Yes.
Okay.
It's interesting.
I didn't know that.
And we now know with data from CME and OCC, you guys know what I'm talking about, that 1/3 of all transactions on the exchange are related to options from some form of dealer hedging their risk on those options. So every third trade you see is a dealer doing something related to options. The market is beyond enormous.
Oh, yeah, it
So
is.
if you get in this case as if you have a stock with a dividend and you get closer to the expiration, you got a large number of options compared to the number of shares outstanding. The fact that you can profit this way is going to exert pressure in the marketplace to drive that stock price up.
Yep. Mm-hmm.
And then perhaps to get enough of an effect, you have to actually model that, or you start with a basic simple model, but then in reality, you need to begin to try to model.
Now you're talking trading.
Yeah, there are models where you can look at the correlations. And again, that's a more advanced topic that you probably need more than mdarray.
And just a quick note, we've got about a half hour left. So
Oh, okay.
we do get kicked out of here at 8:30 hard now. So.
Oh, okay, all right. Yeah, no, I enjoyed the freewheeling discussion, so it's, yeah. Okay, so just one thing to note here is this is what's called the optimal early exercise boundary. So in this region here, it is going to be optimal to exercise. And so you see this in lattices. So for call options, you'll see it up here in the upper region, and for put options, you'll see it down here in this region. Okay, so now we're actually going to look at how we use mdarray to solve this problem. So I actually was around for this crash, October, Black Monday, 1987. In fact, I'd gotten a job offer. I was just out of graduate school with a trust bank. And then this hit. It's like, are they going to rescind the offer? Fortunately, they didn't. So I was able to take the job. But yeah, I was unsure there for a minute. Okay, so we're now going to look at how we implement this. So there are going to be several classes involved here. First of all, we're going to have a vanilla option class. This does not perform any valuation. It just holds information that's needed when it goes into the lattice pricer. It will hold a payoff resource, which is determinate runtime with polymorphism. and it will also hold the time to expiration. The payoff resource represents the payoff of the option. So it can be a call or put, but it's determined dynamically. So again, the lattice doesn't care. It will also, it will hold the contractual strike price and there'll be an accessor on it. So the lattice model will be able to get it. And it will just return the payoff. Actually, that's what the model needs, is just the payoff given the market share price or the share price at a particular node. So projected in the future. So we have something that looks like this. So I've got a unique pointer, the payoff on vanilla option. It will return the time to expiration, and there's the payoff is actually comes from the payoff member. But this is kind of background stuff. We're not going to get into implementation of these classes. It's just they exist and we're going to use them. What we're really interested in is down here, and this is the binomial lattice pricer. And so you can see it's going to hold an MD array, and it's a binomial lattice. So, it's just in 2 dimensions. So we'll have 2 extents. This case, I'm using. Sorry, this is the size T. This is the index, not what it holds. This can be a little confusing. Sorry, a lot of this is still a little bit new to me, so I apologize for hiccups. So it's going to hold an MD array with a node struct, and that struct will just hold the value of the stock at a certain node and the value of the payoff. And then, as you can see here, this is the node struct. Oops. And so they're all connected here with the lattice pricer taking in a vanilla option and with all this information here. Okay, so if we put this into a 2-dimensional array in C++, we can arrange it a little bit differently. So we just use this first row here. These are all up movements here, and then we have down movement here. And so what you can do is project an up movement from each element, as you see here. And then the only down movements we need are the final nodes in each column. Now, I did notice after the fact, after I put this together and used the textbook version of binomial lattice, I noticed, well, yeah, this $32 is the same as here, and this $26.20 you could grab from here. So if you want to be a little more elegant, you could do that. Okay, the binomial lattice pricer class, just look at the declaration here. Again, this is where MD array is the crucial element. So the constructor is going to take in a vanilla option object that holds the payoff. We're going to take it in by move because the option holds a pointer. I'll come back to this this enum class in a second. The lattice constructor will also take in this additional data, this is the volatility, interest rate, dividend rate, and the number of time steps that we want for our lattice. there's a calc price function, it's a public member function here, which will take in the market spot price, the underlying stock, and then the option type, which can be European or American. So also takes in the spot price. In reality, if you were using something like this with a trading system, you might have an interface to a live market feed. And in that case, this argument just might be automatically populated for you from live market data. Okay. The node struct again holds the value of the underlying share price and then the payoffs that are calculated on the return trip. And then the MD array will store the lattice dynamically. So it has two extents, but the size of each extent is determined dynamically, and that's why we use the dextents parameter here. And as I said before, each node stores the underlying and payoff values. Looking at the implementation, we'll just use these variable names for the interest rate, dividend rate, volatility, and time step length. And just to recap, here are the calculations we need to do for the up and down movements and the probability. In the constructor of the binomial lattice pricer class, most notably, it will initialize the MD array member, which we call grid underscore. Also, in the body of the constructor, we'll run these calculations, and then they'll be stored as members on the object, as well as the discount factor, because we will need these going forward at each node U and D. We'll need P going back as well as the discount factor. So we just store them as members. And we get those from these calculations that we noted earlier. Okay, so again, it's divided into two steps. We need to project prices into the future. Let's see. So it's going to be that function, which we call project prices. And then we're going to traverse the lattice back in time. And for that, we'll need to know the option type. So if it's European, we just calculate the expected payoffs. If it's American, we need to check if it's optimal to exercise. So if we look at the project prices function, and this is not the C++, is not all that sophisticated, but what I'll do here is I'll just put the results in advance and then just go through what happens here. So let's see. So again, our initial share price is 32, which we set on the grid at index 00. Then we're going to iterate first by column and then by row. So we go to the next column and then by row, and we apply the up movement and the down movement to each corresponding node in the next step. And we just continue doing this, and at each step we put that price value on the underlying value on the node struct at each node. So we just keep going again until we get to expiration.
I'm curious about something. What do you do with the blank entries? Are they represented by nans, or do you just not ever visit them in the algorithm, so it doesn't matter what they are? Or just curious.
I'm just assuming everything is, we have the numbers. Just, again, if I were to put in exceptions and things like that, it would just kind of cloud the
All
main
right, I
point.
was just curious what you.
I mean, yeah, in practice, yeah, you'd need to handle that.
Since this is really just a one-dimensional array that is getting remapped with the mdspan, couldn't you just write your own that just knew that each row was one shorter than the one before it?
Well, no, this is
Space or,
first, this is mdarray, it's not mdspan.
okay, MD array. But I mean,
So we don't,
own array math, so you
So-
skip the empty cells?
if you want to, if you, you'd have to look and see if it's worth it or not. mdarray is there waiting for you. You don't have to develop it.
Chances are, if you were really doing this, you wouldn't be doing it for only 5 time periods. You'd be doing it for 365 time
Yeah,
periods.
we're getting to that.
Okay. Yeah, because all of a sudden that starts making a lot of empty spaces.
Yeah, I mean, again, it comes down to how much better does it perform? You know, for some things, this could be perfectly adequate. Other cases, high frequency trading or something like that. Yeah, then you might want to look at something different. So anyway, here you get the projected share prices at the option expiration. Just one thing to note is that here, notice that we're using the round bracket operator for mdarray, but starting in C++ 23, we'll have the square bracket array for multiple indices, which will be a nice addition finally. Then iterating back in time, we're going to calculate the payoffs. So again, I'll just put the original prices, and then these are the same payoffs that we got with the American option earlier. So we're going to move backward in time now. And so we start in the last column. Let's see. And then we're going to move back and start by, again, iterate by column. Then we're going to calculate the discounted expected payoff for each node, but we're going to check to see if it's optimal to exercise at that point. The values here are those that it accounts for early exercise. But if it's an American option, then it's here that we check it. So if our actual payoff is greater, then we reset the payoff value. Again, from our previous diagram, you can see that we have the optimal values here and here. And then at the final position, as we move back in time, we arrive at the price of the American option, which we saw earlier was $3.34. So that is the idea behind using mdarray for a binomial lattice. There are other types of lattices. One is a trinomial lattice, and these are common in option pricing problems where you're dealing with stochastic interest rates or something like variable volatility models. So these start getting more interesting mathematically. So it might look something like this. So you have an up movement, a down movement, and then you just carry this price forward in the middle. That would actually be an easier case of carrying them forward in your program. So you compute up and down values here, and then just carry the 100 forward here. In the next step, we only need to compute the up value. We carry the middle value forward, and that's the case until we get to the last node where we have to calculate the up and down values. And so we just keep going. In our code, then we would have something like this. So we add the 2 time points. You can also have options involving higher dimensions, and this is where you have options on more than one security. So for example, payoffs you might have the maximum price of 2 equities. That would be your payoff. Or you might have the maximum of 3. Or you might have, say, a call option on the maximum of 2 asset prices. So as you see here, it's going to be the max value of all of these, then less the exercise price. For a price projection of 2 assets, now it becomes a bit more of a sophisticated problem. But that's how you could visualize it. And so now we just add on a 3rd dimension of length of equal to the number of time points. And so now we have 3 extents instead of 2. Okay, now we're going to get to Chris's question about convergence. So in realistic applications, we're going to need more steps and nodes for the price to actually converge to something meaningful. So yes, we can take this out to more and more time steps and nodes, but the problem we get is the results tend to oscillate. So even as we get out here to 300 time steps, we're still getting this oscillating pattern.
Why does it oscillate?
Just the nature of the model, the math behind it.
All right, because I see something like that, I suspect round off here.
No, this is based on the theory.
Okay, that's interesting.
So what you can do is you can mitigate this by taking the average of the result from n and n plus 1 time steps, and then that will get better convergence. Typical range is what you see here, and from about 50 to 350, but it comes with a caveat. It is going to depend upon the type and terms of the option. But when you do that, as you can see, we get better convergence. And then I just ran a quick example using the previous example, but starting with 65 time steps and taking it out to 75. So this is where we put everything together. We have the payoff that's moved into the option object, and then it's moved here into the lattice pricer. Then here, we compute the average and stick that into a vector, which we'll access later. And our price will be the last element of this vector. And so running this, just some results. Again, the code here for you guys is, it's not that exciting, but what's interesting is to see the difference here. So this is just running one at a time with increasing values of n. And you can see there's a bit of oscillation here. But when we look at the average values, we can see we're converging to something meaningful. And just as an aside, when we just used the 4 time steps, we had an option value of $3.34. So that's actually a pretty significant difference. Yeah, I'm almost done. Okay, so just to wind up here, the good news is over time, we may have market crashes. For example, this is
That's the good news?
yeah, that's. Well, no, we have the crash here.
Depends if you're selling short.
Wait, but, you know, if don't panic, and over time, generally, you're going to go up. Now, I'm not here to give investment advice. I just, in fairness, to contrast with the, kind of the depressing photos I used earlier. Okay, first of all, some references. So I used a number of figures from this book by Peter James. And if you're interested in learning about option theory, this is a really, really good book. It's mathematical, so you've been warned, but it doesn't go crazy like into the deep details of measure theory, because you really don't need it for you don't need to get into it unless you start getting into stochastic interest rates. But it's a really, really nice book. The other book is this book by Liu, and I took one of the figures from this book earlier on, the payoff versus the option value figure. I actually used both of these books when I was teaching, as well as for C++, I used both of them, plus this book by Mark Joshi. This was actually published in 2008, so it didn't include the new features since C++ 11. Unfortunately, the author passed away in 2017, so it's probably not going to be updated by anyone for C++ 11 and after. But what I did in the presentation, just again, in case you're interested, I used a unique pointer in place of a raw pointer, which is what Joshi uses. Yeah, so keeping it modern. Another cool thing about that is he uses virtual constructors. And so when you do that, you end up with object copy, but with unique pointer, you don't. So that's another cool thing. So I don't know, maybe in my spare time, maybe I'll rewrite some of this with modern C++. I don't have anything else to do. But anyway, all three of these are really good books. Also, very important reference is the actual proposal 1684. And so you can have a look at it if you want. I'd also like to just say special thanks to Mark Homan, who's a co-author. He helped me a lot with working through mdarray. He's also helped me quite a bit with a chapter in my book where I discuss some of the new linear algebra features that are coming down the pike in C++, or in C++ 26. So summarize, mdspan is coming. A lot of people are excited about it. At CPPCon last year, there's several talks about it, a lot of buzz. mdarray is expected another 3 years, but again, you can try it out. And it's useful for where you don't know the data in advance, and it's essentially ready-made for lattice models like we just worked through, and in particular, American option pricing, because we can evaluate optimal early exercise. They're also, because it's a generic multidimensional array, we can also extend it, say, to a trinomial lattice, which would allow us to handle stochastic interest rates and stochastic volatility. And it can be extended to 3 or more dimensions for some of these payoffs that we looked at earlier. But if you get, I don't know where the exact number is, but if you start getting, say, above 3 assets, you're going to be eventually get hit with the curse of dimensionality. And so in that case, you might want to move towards a Monte Carlo based model. Also, in these cases, you would have to modify the node object to handle more than one asset price being projected. Okay, so if you're interested in learning more, you can contact me. You can reach me at CPPCon. I am, as far as I know, still the student program advisor. I should be there in October. I'm also on LinkedIn, so that's another way to get in touch with me. So anyway, that's it. So thank you very much.
Thank you, Daniel.
Yeah, thank you.
Thanks.
I learned a lot about.
And if you do, we don't have a whole lot of time, but
Yep, we got 7 minutes.
so if you do have any
Q&A questions.
What Walter was talking about before with the actual derivatives or getting paid out on certain, or not the dividends, getting paid out on certain things, that actually would create an artificial ramp of the stock price right before they're
Yes,
issued, and then it drops after.
yes, that's what.
So there's other formulas that would take that into account for when you're.
Yeah, you can use a lattice for that. That's all in the James book. And I was going to say, I don't know if any of you here are students or on the faculty at University of Washington, you can get all 3 of those books for free in PDF form. No.
And Bob's got a question on.
Okay, yeah.
Yeah, I have years ago made extensive use of Boost's version of this,
Yeah.
which is a multi-array ref for which is the non-owning version of this.
Mhm.
And I was using 4-dimensional arrays to do signal processing with, the dimensions were delay and Doppler and channel and whatever. And I found, unfortunately, that it took forever to compute the indices. That Boost's version of this, at least, unless I went outside the multi-array structure, it was just took all of its time computing the indices and was very inefficient. You know, if there's anything in the new mdarray proposal that, for example, gives you iterators over 1 dimension or specialized iterators for a subset of the dimensions or something like that, that might be less, a little bit less computationally inefficient.
I'm not sure.
I have a little bit of knowledge in that area. First of all, I don't know why calculating indices should take very long. It's all integer math and mods and stuff. But as far as iterators, because you're dealing with multiple dimensions, the whole question came up, well, how do you want to iterate it? You row major, column major, depth major. And so they allowed multiple different types of iterators that could actually be a Manhattan distance, which is like square blocks. So you're actually working your way out from a certain point in circular forms, or
I'm thinking of iterators that are constrained to 1 dimension or a subset of dimensions. What happens is for every combination of 4 indices that I was using, it went through the entire calculation of the amount of the step for the first index times that index plus the step for the second index times that. So you're doing this entire calculation for all of the indices in order to select one item from that four-dimensional structure.
I know mdspan has sub mdspan. So you can do that. I don't know what's planned for mdarray. I suppose there will be something like that.
When you're saying one dimension, you want to take the raw underlying data and just walk through it raw?
Well, you can do that with the
Okay, so
raw
I'm
underlying
confused when
data.
you're
It's not
saying what
easy.
you wanted is a one dimension.
What I wanted to do is iterate through one of the dimensions while leaving the other dimensions fixed and do it efficiently.
Right. Hey, Bob, one other thing to watch for that, because I've run into this before, is make sure you pick your row major or column major or depth major to match, because cache coherency will kill you if you get that wrong.
Yeah,
It's
I'm aware of that, and I did pay attention to that, but
Okay,
it's not the cache coherency, it's just computing the index that
Okay.
killed me. So I stopped using it.
Yeah, well, for what it's worth, I've used it for some option examples like this and, ran it out to like 300 time steps and even did the averaging, and it's just on a laptop, and it ran quite fast.
Well, the key difference is the number of dimensions. When you get beyond 2 dimensions, then it gets really slow.
Yeah, that could be. And that's why I mentioned that if you get above, if you get above 3, then you might want to start looking at least for option pricing, you might want to look at Monte Carlo based models.
Hey, folks, just a note, we got about 1 to 2 minutes left, so we should wrap up here. Okay.
Well, good to see you, Bob.
Yep. Okay. So, go ahead and let Kaylee know she can kill the.
Thanks again for presenting.